the second presentation. Konrad Czerski, please, your presentation. And Konrad Czerski from the University of Szczecin, Poland. And please, Czerski. Oh,
yeah,
thank you. Thank you.
Thank you very much. I would like to present you today very briefly our new project in the European Union. We've got some money for next 4 years, and the objectives of this project is very simple. So we want to understand the phenomena leading to the cold fusion in both systems, proton-induced and neutron-induced. And for that, we wanted to combine gas loading experiments. So it is very nice that I can speak now after Professor Iwamura about it, and accelerator experiments that give us information about tunneling effect, about screening effect in different materials. So here we work in the consortium of 16 different institutions, scientific institutions. There are universities and commercial companies. In Europe, there are some regional parts of this consortium. There is northern part of Europe. There is Sweden, Poland, Germany, and Slovenia. South part of this project is Italy, many laboratories you can see here in the list on the right, and France and Belgium working also together. So there are 16 different institutions. 16 means there are some so-called third-party institution as MIT and Lakehead University, and lately also the University of Iceland. There are additional partners here in this consortium. And inspiration for this kind of experiments was, of course, the results of Japanese experiments, gas loading experiments in the past. There are very nice papers of Kitamura and Iwamura. You have heard just about it, so I don't need to present it in details. The point is, however, that in Europe there are also the history of this kind of experiment, gas loading experiments, is very long, and there are many experimental results in European laboratories. You have here some examples of that. Francesco Celani, Jean-Paul Biberian, Piantelli. So there are some very interesting results, and they are very interesting because it could be much easier to apply this kind of reactors for commercial applications. Okay, so compared to the let's say heavy water experiments in the past. Okay, so let me say something. What is the reason why we think we can think about explanation of this effects? So the key effect is a tunnel effect, of course, if we speak about nuclear-induced reactions, and if we want to explain this high heat excess observed in different experiments. So, as said before, we need to overcome the Coulomb barrier, and usually for that you have this penetration coefficient that describes the probability to tunnel the Coulomb barrier. And the problem is, of course, that we speak about very low temperatures compared to the solar temperatures of 50 million degrees, or if you're speaking about hot million degrees. So the problem is to explain it, how the particles can go through the barrier at very low temperatures. And the solution for that is the electron screening. So we studied the nuclear reactions inside of different environments, and what I can say, the metallic environments can enhance very strongly the nuclear reactions at very low energies. The mechanism for that is that the electrons can shield the Coulomb barrier, the repulsive force, Coulomb force, and this can be described in the case of the potential using special component here, the screening factor that can be described by the screening energy as a constant value with the screening length A here. And you have the charges of the, including particles, reacting particles Z1 and Z2. So it is very easy to, let's say, to describe it theoretically, because in this case, we can change the penetration factor. Here you see on the left, just you can put the screening energy UE to the our kinetic energy, but only in the penetration factor. There's not a physical kinetic energy, there's only mathematical description for that. Okay, and some very old experimental results that illustrate the screening effect in the nuclear reactions. It was made in high vacuum systems, setups. This is very important because we are at very low energies, and every contamination of the surface, of the target surface, can reduce the effect. So you see here our first results already in the 90s, last century, and then we could present you that the screening energy is dependent on the hosting material, aluminum, zirconium, and tantalum, and this compared the screening energy, this additional shift in the penetration factor is much higher compared to the gas target experiments. So this is a kind of comparison between theoretical values and experimental values. You see we've got that time very high screening energies, palladium, tantalum, 300 electron volts compared to the 100 electron volts theoretically predicted. And then if you present it in the dependence on the electron gas parameter, you see that this target dependence can be explained very well, but this missing factor 2, 3 between theory and experiment. So therefore, we think that using this screening effect and some other effects that can enhance nuclear reactions at very low energies, as let's say some phonon coupling experiments or phenomena or other coherent states, for instance, can enhance additionally the reaction rates at very low energies. But the main effect should be electron screening that could be measured in accelerator experiments very precisely. Once again, so our idea was to combine these gas loading experiments with accelerator experiments in order to understand the theoretical point of view, or what is the reason for so high reaction rates. So we are looking for the best powder and bulk materials for that. And this theory I have already mentioned. And finally, what we want to do is to optimize future hydrogen metal energy reactor. Okay, so there is a kind of experiments we want to perform at the University of Szczecin, and we've done already some of them. There is a direct kinematics experiments using accelerator. You see here our accelerator, and our chamber. It is, we will use now ultra high vacuum 10 to minus 11 millibar, and there are several groups in our consortium working on that. There is also Future On group from Italy, and inverse kinematics will be measured in Joseph Stefan Institute in Slovenia by Professor Lipoglavsek. Okay, so there is just general information, and then I would like to present you our last results that the very precise measurements made on zirconium 2-3 years ago. And you see that this enhancement, because you see here this enhancement factor and dependence on neutron energy, we can describe this enhancement using string energy. There's this blue line, but this description is not correct, it's not well enough. You see there are some points which are systematically below or above the curve, depending on the neutron energy. So what is necessary to include additional contribution, and is the resonance contribution. We are speaking about it already for many years. And this just experimental results that should say us this resonance, threshold resonance in helium-4 compound nucleus should take place. So in this case, finally, at very ultra high vacuum conditions, we get screening energy 110 electron volts, which is very close to a theoretical one we have predicted many years ago. And the resonance width for the proton channel, because there's neutron-proton reaction on neutrons, this 20 millielectron, very small value, but this resonance should have single particle characteristics, and therefore there is only one open channel, neutron channel for that. We could describe this interference effect between resonance and the other reaction channels here using phase shift, and so I haven't time to discuss in detail, but the fact which is very important for understanding the experimental results, this presented also here in this diagram. We have measured the screening energy or enhancement factor during the time impinging neutrons on the target within 24 hours. And you see that enhancement factor depends on the time. So the largest one was after 4 hours of irradiation. And continuously, we have measured also the composition of this surface, let's say, so we could see that there is a little bit oxygen or carbon layer, very small, less than one atomic layer on the surface. This so we could say that the result for this time dependence of the enhancement factor is the number of impurities and crystal defects.
Only 5 minutes. Only 5
okay,
minutes.
I am just, I will finish now. Okay, so it means that we've measured for our precise measurements just very, very shortly after cleaning of the targets. So it means there's this first point, but if we will wait a little bit longer, we will get more larger screening effect and enhancement factor. It means that our screening energy can be changed between 150 electron volts, and you can see here what does it mean. So here on the left, you see the cross-section calculated using this resonance, threshold resonance at very low energies, thermal energies. And this is the effect of the penetration. So of course, if the energy of deuterons will be higher, the cross-section will increase very quickly. But you see that the contribution of the resonance depends on the screening energy. This the upper curve, it is for 300 electron volts. It is a factor of 10 orders of magnitude higher than if you will have only 100 electron volts. And the resonance contribution will increase the cross-section once again by a factor of about 7 orders of magnitude. So in the past, we presented the D reactions depending on screening energy at room temperatures. And our conclusion was that the screening energy can explain Jones' measurements of neutrons. You know, it was a very nice measurement in 1990. But Fleischmann and Pons, it was 7 orders of magnitude higher. So, but using this resonance effect in the compound nucleus, we can explain also heat excess experiment by Fleischmann and Pons now. Okay, so there is a very short our time schedule of our project. Once again, accelerator experiment, gas loading experiments at solid bulk materials and powder materials, both hydrogen-induced and deuteron-induced theory that should combine both effects, and of course report dissemination. This is just usual situation. And finally, what I should mention here, we want to present new solution for new construction of new reactor, where the company Vegatech and Future are contributed. Okay, then finally, problems we want to solve. Once again, oh, sorry. There's electron screening and the role of impurities in the crystal and crystal defects. We have already first results using positron annihilation spectroscopy that confirm this defects effect. Nuclear reaction induced by protons and neutrons, but the role of lithium isotopes is very important because then proton-induced reaction can be here contributed. And the third point is, of course, nanostructure powders. And our approach, it means that we should have materials which with very large density of the crystal defects. So nanostructure powders is just a very good material for that. Because once again, this crystal defects effect enhance the screening energy, and then we can obtain a large amount of heat excess. Okay, that's all I wanted to present you today. So thank you very much.
Thank you very much for your very interesting presentation. And we have small time, only short question, maybe 1, 2. Any question, please? I have no question, and I have a small question for you, Professor Czerski. Please show once more the picture with experimental results. Is this one? What? Once more, previous.
Okay, so you see once again.
No, not that previous picture.
This one?
No. What was this one? Yes, I understand very good the horizon of this